Hello, my name is Martin Kujawinski, and today I'm going to be demonstrating my final project for 4J03. So first I'm just going to show off what my main function here does. It's basically implementing the algorithm, and I hard-coded the input because it was not really a requirement to make this project interactive with user input. So just to make it easier on myself, I hard coded some input, and it wasn't necessary, but just for fun, I implemented like you could put in fractions for probabilities, and also it will check that your words in your Huffman code uh, will be one character long, and that your probabilities add up to one. Because if they don't add up to one, then obviously Huffman coding does not make much sense. So once we have our two-dimensional string array for our input, we validate it, and if it's valid, we run the algorithm. And to do that, we basically make an object Huffman with our input, and then we simply run the coding method. This runs the algorithm, and it will return an array with with are just an array of the paths required to get to the words and their correlated probability. So basically, it'll just basically be what our input was, but with a third entry of our path. So like 0, 1, 0, 0, 0, 1, etc. Like the Huffman coding. Now, what I implemented kind of as a bonus is I made a method that will make a linear combination of every letter. So like AA, AB, AC, AD, AE, AF, BA, BB, etc. And their corresponding probabilities. That's what this method does. And then it calculates a new result for the now longer input. Ignore this code. This code is for interactivity, but I don't think it's necessary for the project. And here we just print out all our outputs. Uh, if you notice here, I actually did make a method that calculates the entropy. So, and a method that will calculate the expected length of your path. So when I run it, it'll be more obvious what I mean. So here we'll run the code. And let's expand this. So as you can see, here's our input that I hard coded. The calculated entropy of these probabilities, which is the formula, obviously, pi times log, the sum of pi times log of 1 over log 2 base 2 of 1 over pi. So that's the entropy there. And after running the algorithm, these are the paths to f. So f is the most likely one. It has the highest probability. That's why it has the shortest path, obviously. And as you can see, each letter has a corresponding path. And when we calculated the expected length, which is simply the sum of the length of this path times the probability, we get 2.2, which is pretty close to the entropy, but we can do better by doing a combination input. Like I said earlier, AA, AB, AC, AD, etc. goes on for a while. We have an improved output. And this output also produces paths, obviously. And if you want, you can go check all those paths. And now if we calculate the improved expected length, we have this. And obviously this length is for words that are of length 2. So if we divide it by 2, we have a new expected length. This is the expected length of a path per character, 2.17, which as you can see is a better expected length than 2.2. It's closer to our original entropy. So that's basically what my code does. Now I will try to quickly go through how it does it. So once it gets the input, it creates an object Huffman. And here's the constructor for Huffman. Basically, all it does is it transfers the probability and the word into and makes it a list string. It makes it a string list. And then it makes a list of every string, of every list. So a list of lists, pretty much. After this is the code that does this, and then after it does that, it converts every sublist into just a type pair, a list pair. This is just to make stuff easier later on. But all you really need to know is that this constructor basically makes a list of pairs, and a pair is a word and a probability, and basically that's it. And it stores it in data. It can also so now we can go into the actual algorithm. So we have a list of pairs, right? But we need a list of nodes because the way the algorithm works is it'll take the two smallest probabilities, combine them, and then go from there. So this code here, this line, I'll go to the class path pair later, but all it does is it adds a third entry. So right now we have a word, we have a probability, but this code will add this third entry, which is just a blank path, because at the start of the algorithm, we don't have a path yet. And that's all this for loop does. It's adding this blank path to every pair of data. Now, once it's sorted, we sort the list by ascending probability. So the first entry in the list will be the smallest probability entry. Since we know this, we know that the first entry in the tree will have the lowest probability. We store that probability, and then we set the path of that entry to 0. Every path in that node is set to 0. Then we get rid of that node from the tree, and we do it again. But this time, since this would be the second least probable probability, we set this path to 1. That's just how the algorithm works. Now that we combine these two nodes here, basically, and then we add it back into the tree, that's once we remove them, we combine them, we add the probabilities, that's what this, sorry. One of these lines here adds the probabilities of the two nodes together, and then adds the new node back into the tree, and then sorts the tree again, because that node may not belong at the end of the list. And since we know that this algorithm has to run n-1 times, because each time you're taking two nodes and putting them together to make one node. So therefore, we end when there's only one node left, which would be n-1 times, n being the length of your data set. So once this all runs, we should now have one node of probability 1, because that's all the probabilities together, and we just do a for loop here. The final resort is generate array, which is just a sub function here that basically just puts every entry from the node into its corresponding array slot. And then once that's generated, it just returns that array. And that's pretty much the bulk of the code. I use a couple of other classes and objects like node. A node is basically a probability, which is the probability that is correlated to that node, and a list contains. And contains is a path pair. A path pair is basically a word, a probability, and a path. So each node might have multiple path pairs because it could be like the fourth step of the algorithm, for example. And after 4 steps, you might have 4 branches. So basically, this list here is like the different branches you have. And that's pretty much it. If you have any questions, feel free to email or anything. And thank you for your time. So again, yep, thank you.